Hello, friends. Disclaimer. As an Amazon associate, I earn from qualifying purchases at no additional cost to you. Please don't forget to check out product links for stargazing in the description of the video. Imagine staring up at the night sky, gazing at a faint smudge that, to the naked eye, might not seem very significant. Yet, that tiny blur is the Andromeda Galaxy, a massive collection of stars, gas, dust, and dark matter lying approximately 2.537 million light-years away. This neighboring galaxy is the closest spiral galaxy to our Milky Way and is on a slow collision course with us, predicted to merge in about 4.5 billion years. The Andromeda Galaxy, also known as M31, spans over 220,000 light-years in diameter, nearly double the size of our Milky Way, and contains roughly 1 trillion stars, twice the number in our galaxy. The Andromeda Galaxy did not form in an instant. It is the result of billions of years of cosmic evolution. Around 10 billion years ago, during the era known as the Cosmic Noon, galaxies like Andromeda began forming from the gravitational collapse of gas clouds, which led to the formation of stars, star clusters, and eventually galactic structures. Over time, Andromeda likely merged with smaller galaxies, absorbing their stars, gas, and dark matter. These galactic mergers contributed to its present size and mass. The evolution of Andromeda has also been influenced by various cosmic events such as supernova explosions, which enriched its interstellar medium with heavy elements necessary for planet formation. The galaxy's history is written in its stars. Older stars tend to be found in its central bulge, while younger, more massive stars populate the spiral arms. By studying the chemical composition and distribution of these stars, astronomers can piece together the galaxy's past, tracing back to its earliest days. When comparing Andromeda with our own Milky Way, there are striking similarities and significant differences. Both are large spiral galaxies with a similar structure of a central bulge, disk, and halo. However, Andromeda is more massive and hosts more stars. It also displays a higher rate of star formation, particularly in its spiral arms. Despite these differences, the two galaxies are gravitationally bound and will eventually collide, a cosmic event known as the Milkomeda merger. The dynamics of both galaxies' interactions with their satellite galaxies also offer fascinating insights. Andromeda has over 50 satellite galaxies, including well-known ones like M32 and M110. These smaller galaxies orbit Andromeda, occasionally plunging through its disk, triggering bursts of star formation and shaping the spiral structure through gravitational interactions. These processes are also mirrored in the Milky Way, where satellite galaxies like the Large and Small Magellanic Clouds interact with the galaxy, leaving streams of stars in their wake. One of the most fascinating and inevitable events in the distant future is the collision between the Milky Way and Andromeda galaxies. Despite the vast distances in space, these two galaxies are slowly being drawn toward each other by mutual gravitational attraction. Current estimates predict that in about 4.5 billion years, the two galaxies will collide, resulting in a spectacular cosmic event. However, contrary to what one might imagine, this galactic collision won't involve stars smashing into each other. Due to the vast spaces between stars, direct collisions are incredibly unlikely. Instead, the gravitational forces will distort both galaxies, flinging stars into new orbits, triggering bursts of star formation, and eventually leading to the creation of a new galaxy often dubbed Milkomeda. During the collision, Andromeda's spiral arms will be torn apart, and its central core will merge with that of the Milky Way. The supermassive black holes at the centers of both galaxies will likely merge as well, forming an even larger black hole. The resulting galaxy will have an elliptical shape, and over time the gas and dust needed for star formation will be used up. leaving behind an old, dim, and relatively inactive galaxy. The night sky on Earth, if our planet still exists by then, will be completely transformed, with Andromeda dominating the horizon, eventually merging into a brilliant cosmic spectacle as the galaxies collide. Andromeda is surrounded by a number of satellite galaxies, the most notable being M32 and M110. These dwarf galaxies orbit Andromeda and play a significant role in its dynamics. M32 is a compact elliptical galaxy with a dense population of older stars, suggesting that it may have once been a larger galaxy, stripped of much of its material through interactions with Andromeda. This stripping process left behind a dense core, which we observe today. M110, on the other hand, is a dwarf elliptical galaxy that still retains a significant amount of gas and dust, indicating ongoing star formation. The interactions between these satellite galaxies and Andromeda have influenced its spiral structure, triggered star formation, and contributed to the complex gravitational dance occurring in this region of space. The study of these satellite galaxies helps astronomers understand the processes of galactic evolution and how larger galaxies grow by accreting smaller ones. Stars within the Andromeda Galaxy undergo a fascinating life cycle that spans billions of years. From the birth of a star in a stellar nursery to its eventual death, this cycle is dictated by the star's initial mass. In Andromeda, star formation is particularly active in the spiral arms, where dense clouds of gas and dust collapse under gravity, sparking nuclear fusion. These newly formed stars range from small, long-living red dwarfs to massive, short-lived blue giants. As stars age, they undergo significant changes, expanding into red giants as they exhaust their hydrogen fuel. For the most massive stars, this process culminates in a dramatic supernova explosion, scattering heavy elements into space and leaving behind neutron stars or black holes. These elements are crucial for forming new generations of stars, planets, and even life. In Andromeda, the cycle of star birth and death is a key driver of its evolution, continuously reshaping its structure and contributing to the galaxy's vibrant colors visible in telescopic images. Galactic archaeology is a field dedicated to unraveling the histories of galaxies like Andromeda by studying their oldest stars, globular clusters, and stellar streams. By analyzing the chemical compositions, ages, and velocities of these ancient stars, scientists can reconstruct events from billions of years ago. For example, certain stellar populations in Andromeda's halo are thought to be remnants of smaller galaxies that were absorbed by Andromeda long ago. One of the most striking discoveries in Andromeda is the presence of large, faint stellar streams that arc through its halo. These streams are the remnants of dwarf galaxies that have been torn apart by Andromeda's gravity. By mapping these streams, astronomers can infer the properties of both the dwarf galaxies and Andromeda's dark matter halo, which governs the movement of these stars. Additionally, globular clusters, dense collections of ancient stars, serve as time capsules, preserving information about the conditions in Andromeda's early years. These clusters are some of the oldest structures in the galaxy, dating back to its formation. By studying them, we gain insights into the initial stages of galaxy formation and the processes that shaped Andromeda's evolution. Within Andromeda's trillion stars lie countless exoplanets, worlds that could be similar to those found in the Milky Way. The study of these exoplanets is a rapidly growing field, driven by advances in telescopes and observational techniques. If we could one day observe these planets in detail, what might we find? Would there be Earth-like worlds with liquid water, or gas giants with storm systems larger than Jupiter's Great Red Spot? The diversity of planetary systems in Andromeda could rival or even exceed that of the Milky Way. Planets in habitable zones, where conditions might support life, are of particular interest. These zones vary depending on the type of star. For example, planets orbiting a cooler red dwarf might need to be much closer to their star to maintain liquid water, while those orbiting hotter stars might need to be further out. In the future, space telescopes capable of direct imaging might allow us to see these distant worlds with clarity, identifying atmospheres, weather patterns, and even potential signs of life. For now, much of this remains speculative, but every new discovery within our galaxy brings us one step closer to understanding the broader possibilities in galaxies like Andromeda. As we expand our understanding of the universe, the idea of intergalactic travel becomes more tantalizing, especially when considering destinations like Andromeda. Wormholes, hypothetical shortcuts through space-time, are one of the most discussed concepts in this regard. These theoretical passages could, in principle, allow faster-than-light travel by connecting two distant points in space, enabling a traveler to reach Andromeda in a fraction of the time it would take using conventional methods. The concept of a wormhole is rooted in Einstein's theory of general relativity, which describes how massive objects curve space-time. If 2 points in space-time could be connected through a tunnel-like structure, a spacecraft might be able to pass through, effectively bypassing the distance between galaxies. However, creating or stabilizing a wormhole would require exotic matter with negative energy density, something that remains purely speculative. Even if wormholes or faster-than-light travel were possible, there would be significant challenges. Time dilation, causality violations, and immense energy requirements are just some of the hurdles that would need to be overcome. Despite these challenges, the continued exploration of these concepts pushes the boundaries of our understanding of physics and keeps the dream of intergalactic travel alive. Communication across intergalactic distances poses a significant challenge, given the limitations of light-speed travel. Even a simple message sent from Earth to Andromeda would take 2.5 million years to arrive. However, quantum mechanics, particularly the phenomenon of quantum entanglement, offers a potential, albeit theoretical, solution. In quantum entanglement, two particles become linked in such a way that the state of one particle instantaneously affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein described it, could revolutionize communication if harnessed for intergalactic use. Theoretically, information could be transmitted instantaneously between entangled particles, bypassing the speed of light limit. However, practical applications remain far off, as maintaining entanglement over such vast distances and deciphering the transmitted information are challenges yet to be solved. In addition to quantum entanglement, other speculative ideas, such as neutrino-based communication, are being explored. Neutrinos are nearly massless particles that can travel through matter almost undisturbed, potentially allowing messages to penetrate through dense interstellar or intergalactic obstacles. While still in its infancy, this field of study could one day lead to the development of a communication network that spans not just our galaxy, but others like Andromeda. Traveling to Andromeda is not just a matter of distance and technology. One of the greatest challenges would be the exposure to cosmic radiation. As we move beyond the protective magnetic field of Earth and the Sun, spacecraft and their inhabitants would be subjected to high levels of radiation, including solar wind particles, galactic cosmic rays, and even radiation from distant supernovae. Over intergalactic distances, this radiation could pose severe risks to both human explorers and spacecraft systems. Cosmic rays, which are high-energy particles traveling close to the speed of light, can cause significant damage to biological tissues, leading to increased risks of cancer, DNA damage, and other health issues. Shielding against this radiation is a major concern for any potential intergalactic journey. Various solutions have been proposed, from magnetic fields that could mimic Earth's protective shield to spacecraft designs that incorporate heavy materials or even water layers as radiation barriers. In addition to physical protection, advancements in genetic engineering could also play a role. Some scientists speculate that it might be possible to enhance human DNA to make it more resistant to radiation, or even develop medical treatments that repair radiation-induced damage more effectively. These ideas are still in the realm of speculation, but they highlight the multifaceted challenges of preparing for such an extraordinary journey. One of the most mysterious aspects of Andromeda, like all galaxies, is its dark matter content. Dark matter, an invisible substance that does not emit or absorb light, makes up the majority of Andromeda's mass. It's responsible for the galaxy's rotation curve, the way in which stars and gas move at different distances from the center. Unlike ordinary matter, which is concentrated in the galaxy's visible regions, dark matter forms a vast halo surrounding Andromeda, exerting a gravitational pull that holds the galaxy together. Understanding dark matter is crucial not only for comprehending Andromeda, but for grasping the fundamental nature of the universe. Current theories suggest that dark matter consists of yet undiscovered particles that interact weakly with ordinary matter, making them difficult to detect. Ongoing experiments, such as those using underground detectors and particle accelerators, aim to unlock the secrets of dark matter, which would provide critical insights into how galaxies like Andromeda formed and evolved. Gravitational waves, ripples in the fabric of space-time caused by massive objects accelerating, are a relatively new area of astrophysical study, but they provide vital insights into the behavior of galaxies like Andromeda. These waves were first directly detected in 2015, opening a new window into the cosmos. When large masses such as merging black holes or neutron stars interact, they send out gravitational waves that spread across the universe, including within Andromeda. In Andromeda, gravitational waves likely play a key role in its internal dynamics and interactions with neighboring galaxies. The supermassive black hole at its core, for example, emits these waves as it interacts with surrounding matter or smaller black holes within the galaxy. As Andromeda moves through space and interacts with satellite galaxies, these waves subtly influence its structure and the orbits of stars within it. Although these effects are minuscule on the human scale, they are critical in understanding how galaxies evolve over billions of years. Future observatories like the Laser Interferometer Space Antenna are expected to detect even more subtle gravitational waves, allowing us to study Andromeda's hidden dynamics in unprecedented detail. These discoveries could offer clues about the processes that govern galactic collisions, star formation, and the ultimate fate of galaxies in general. The ultimate fate of Andromeda, like all galaxies, is influenced by the mysterious force known as dark energy. Dark energy is driving the accelerated expansion of the universe, causing galaxies to move away from each other at increasing speeds. Despite this expansion, Andromeda and the Milky Way are moving toward each other due to their mutual gravitational attraction. However, as dark energy continues to dominate the universe, the large-scale structure of the cosmos will change. In a distant future, after the Milkomeda merger, the accelerated expansion driven by dark energy might cause the remnants of Andromeda to become isolated in a dark, empty universe. If dark energy continues to push galaxies apart faster than the speed of light, eventually the light from other galaxies will no longer reach us. The observable universe would shrink, leaving the Milkomeda galaxy alone in an increasingly barren cosmos. This scenario raises profound questions about the long-term future of the universe. If dark energy remains constant, it could lead to a big freeze, where stars gradually burn out and black holes slowly evaporate, leaving behind a cold, dark universe. Andromeda, along with all other galaxies, would eventually fade from view, leaving behind only the remnants of their past brilliance. If intelligent civilizations exist in Andromeda, what might they look like? Given the vast timescales and different evolutionary pressures, life in Andromeda could be radically different from anything we know. Advanced civilizations might harness energy in ways that are beyond our current understanding. For instance, they could build Dyson spheres, massive structures that encompass stars to capture their energy, or even manipulate the fabric of space-time. The Kardashev scale, a method of measuring a civilization's technological advancement based on its energy consumption, offers a framework for imagining such civilizations. A Type 1 civilization harnesses energy at a planetary level, a Type 2 at a stellar level, and a Type 3 at a galactic level. If Andromeda hosts a Type 3 civilization, it could be capable of harnessing the energy of entire star systems, perhaps using the galaxy's central black hole as a power source. However, the existence of such civilizations raises ethical and philosophical questions. Would these civilizations seek to explore and colonize other galaxies, or would they have transcended such goals? Perhaps they would focus inward, exploring virtual realities or higher dimensions. Alternatively, they might prioritize the preservation of knowledge, creating cosmic libraries that endure long after their stars have dimmed. Understanding Andromeda and the larger universe requires grasping the immense timescales involved. Human history spans a few thousand years, a blink in the cosmic timeline. In contrast, the processes shaping galaxies unfold over millions to billions of years. The collision between Andromeda and the Milky Way, while distant in human terms, is merely a moment in the life cycle of galaxies. For any civilization contemplating intergalactic exploration, this raises profound questions about purpose and endurance. Would future humans, or perhaps their AI successors, be willing to commit to missions that take millions of years? Generation ships, with entire civilizations evolving on board, could embark on such missions. But the societal and ethical implications are staggering. How would knowledge be preserved and passed down over such time spans? How would cultural identities evolve? These are not just questions for scientists, but for philosophers, ethicists, and futurists alike. As we conclude our exploration of Andromeda, it's essential to reflect on what such a journey represents. Andromeda is not just a distant galaxy. It's a symbol of the boundless curiosity that drives humanity to explore, discover, and dream. From the earliest stargazers to the astronomers of today, our gaze has always turned skyward, seeking answers to questions about our origins, our future, and our place in the universe. In contemplating the journey to Andromeda, we confront not just technological challenges, but profound philosophical questions. What does it mean to explore a galaxy beyond our own? How do we balance the desire for discovery with the responsibility of stewardship over our home planet? These questions will shape the future of space exploration as we move toward an era where interstellar and possibly intergalactic travel becomes a real consideration. The journey to Andromeda, whether through telescopic study, robotic probes, or perhaps one day human explorers, will be a defining chapter in the story of humanity. It's a journey that stretches across space and time, linking us to the farthest reaches of the cosmos and reminding us of the infinite possibilities that lie ahead. If you're ready to take your stargazing experience to the next level, check out the telescope and binocular through the links in the video description below. As an Amazon associate, I earn from qualifying purchases, but it won't cost you a penny extra. Thank you for joining us on this journey through the Andromeda Galaxy. Please like, comment, and share the video, and please do not forget to subscribe for more videos.